Welcome. In today's video we're going to be looking at the sum of an arithmetic progression, and more importantly we're going to try and derive a formula which will allow us to sum an arithmetic progression with computational ease. So first off, let's begin by understanding what exactly a sum of an arithmetic progression is. So what we're going to say here is let Sn denote the sum of the first n terms of an arithmetic progression. So what does that mean? Well, what we'd have is, for example, S1, S subscript 1, would be the sum of the first 1 terms. And what is the first 1 term? T1. S2 is the sum of the first 2 terms. Hence we have term 1 of the sequence plus term 2 of the arithmetic sequence, so on and so forth. We get S3, which would be the first term in the sequence, second term of the sequence, and the third term of the sequence added together. And if we continue in this fashion, what we say is that the Sn in general is given as T1 plus T2 plus T3 all the way up to some pronumeral or Tn. So let's think of how we're going to derive a formula for Sn. So to begin with, we know that Sn is equal to the sum of our Tn terms. However, if we remember back from what we were doing before, we had that T1 was equal to A, T2 was given by A plus D, T3 was A plus 2D, all the way up to Tn, which was A plus n minus 1D. So how are we going to use this to derive an expression? Because here what we notice, we've got an A plus an A plus an A plus an all the way up to an A here. We've got a D, then we've got plus 2D plus all the way up to n minus 1D. Let's see if we can come up with something. So to do that, I'm going to do something a little bit tricky. I'm going to multiply both sides by 2. So here we've got Sn is equal to this long expression here. I'm going to multiply both sides by 2. And I'm going to rewrite this 2 times this big expression. Instead, I'm going to write it as, you'll notice in red, here is the original expression, A plus D plus A plus 2D. And then in the blue, I have the same expression. I actually have the same expression, but in the reverse order of summation. And remember, when you add things together, it doesn't actually matter the order that you add them. You will still get the same answer. So here, you'll notice I've got A plus n minus 1D at the beginning. And of course, the next term, if I were to, that's that term here at the end. And then I go all the way to A, which is here at the end here. Now, going from this term to this term, you'll notice that here we have n minus 1D, here we have n minus 2D. What does that symbolize? Well, we've gone back D in a sense. So that would be the term just before here in this summation here. Now, you'll ask, well, why did I bother doing that? Well, here's something a little bit interesting. Look at what, oh, by the way, just to clarify, if we went, this was the A n minus 2D, and if we were to go back another step, we'd have A plus n minus 3D here, again, symbolizing we've gone back a further D in our sequence, all the way up until we go to A. So why have I done this? Well, it's actually a bit smart, because you notice here, if I take this term here, the A plus n minus 1D, and I add it to A here, the first term of the red sequence, so the first term of the blue sequence plus the first term of the red sequence, I get A plus A, which should be 2A, plus, and then I'd still have the n minus 1D. If I added the A plus D here, and the A plus D here, sorry, A plus n minus 2D here, you notice I get A plus A, which gives me 2A, and I'd get D plus n minus 2D, and d plus n minus 2d is n minus 1d. In fact, if you continue this pattern all the way up to adding this last term in the red sequence, a n minus 1d, and a here, what you get is in fact 2a plus n minus 1d each time you add the first here, first red term, first blue term gives me this. Second red term plus second blue term gives me 2a plus n minus 1d. Last red term plus last a term gives me 2a n plus n minus 1d. And why is that? Well, because here what happens is each time we go up a jump in the red progression, what ends up happening, we go up by d. But each time we go a step further in the blue progression, we go down by d. So by going up by d and then down by d, we actually end up adding the same number again. Now, how many times do we add it? Well, I can tell you how many times we add it. We add it n times, because remember we were summing n in the first place. We were summing the first n terms here. So what we really have is n lots of this number. And that's exactly what I have here. N times 2a plus n minus 1d. Now that's give 2Sn, so of course this means that Sn is in fact that expression but divided by 2. So here all I've taken is n over 2 by moving this 2 to the other side of the equation. So let's go through an example to formalize what we know here. Find an expression for the sum of the first n positive integers. Find an expression for the sum of the first n even numbers, and find an expression for the sum of the first n odd numbers. Okay, well, let's think about this for a second. The first positive integers, so this is part 1, what we have is that the first term in the sequence is a, and the jump between each term in the sequence, so from 1 to 2, from 2 to 3, is d. That common difference is 1. And so what we're going to do is we're going to take that formula that we just derived previously, and we're going to substitute in a equals 1 and d equals 1 in the formula. So here I've substituted a equals 1 here, and I've substituted d equals 1 here. And then, after some simplification here, you've got 2 plus n minus 1. That just simplifies to n plus 1. And we've got a formula, a very well-known formula, I should say, for the sum of the first n positive integers. N over 2 and n plus 1. And just to make sure that this works, let's take a look at 1 plus 2 plus 3. So 1 plus 2 plus 3 is 6. And if we substitute in 3 into this equation, you get 3 over 2 times 3 plus 1. So you get 3 over 2 here times 4. 3 over 2 times 4 is indeed 6. So it does make sense. So for the even numbers, 2 plus 4 plus 6 plus 8, so we've got to work out a formula for this summation. We've got a is equal to 2 is our first term in the sequence, and a common difference of 2 here. So 2 to 4, 4 to 6, and so on is our common difference. So again, we're going to use this formula, and again, we're going to substitute in our value for a and our value for d. So when we do that, we put in 2 and 2. So here now we have 2 times 2 and times 2 at the end here. This gives us 4 plus 2n minus 2, so that part is 2n minus 2, which simplifies down after some simplification. You actually end up with n times n plus 1. The reason being is that this 2 down the bottom cancels with this 2 and this 2 together, still just leaving the n plus, or 2 plus n minus 1, which is our n plus 1 here. And finally, for the odd numbers is actually a nice little formula that I think is quite clean. For the odd numbers, what we have is we start with 1, and again a common difference of 2. 1, 3, 5 goes up by 2. Again, use the formula. Again, substitute in our a equals 1 and our d equals 2. So here we've got 2 times 1 and an a being a 1 and a 2 for our d here in this expression. And actually what you see here is we've got 2, a nice 2 here, minus, and if you expand this brackets you get minus 2, so those 2 cancel out, and so you're left with just 2n here. N over 2 times 2n gives us just n squared, which is actually quite nice. And to see that, in fact, if you have a look at the sum of the first n terms, you've got, sorry, just the first term, you've got 1. 1 plus 3 is 4, which is a square number. 1 plus 3 plus 5 is 9, again a square number, in fact 3 squared, and that pattern continues forever. So it's a nice little pattern to look at. And finally today we're going to go through one more example that's going to be a little bit more algebraic in its nature. So we're not going to derive a formula, more so we're going to solve for a and d and then compute a particular sum. So let's go through this example. The sum of the first 10 terms of an arithmetic sequence is 110, and the sum of the first 20 terms is 420. Find the sum of the first 30 terms. So what we're going to do in this problem, first we're going to find out our value of a and d based on the first 2 pieces of information here. And then using that value of a and d, we will find the sum of the first 30 terms. So let's do that. So again, we're told that the 10th term is 110 and the 20th term is 420. So again, what we're going to say is we're going to let Sn equal that formula that we came across before. And then we're going to substitute in these 2 pieces of information using this formula here. So here we've got 110, S10 is 110, so here we're going to substitute in n equals 10 in our formula and 110 on the other side. So here you'll notice I've put 10 over 2 here equals 100, and I've substituted in n here as 10. That gives us 110 on this side. And then if you actually simplify this expression just a tad, what you get here is 10a on this side plus 45d just by expanding this side of the brackets. So you get 10a plus 45d is 110. And on this side of the brackets, again, the other piece of information here is we're told S20 equals 420. And so again, you substitute in n equals 20 on this side. And then, of course, when you expand these brackets here, you've got 20 over 2 times 2a. So that's 10 times 2a is 20a. And you've got 10 times 20 minus 1, that's 19. So 10 times 19, which is 190d. And for the time being, this is actually where our understanding of sequences and series is no longer needed in some respect. And the reason I say that is because you'll have a look now, and we've got 2 simultaneous equations, which we could equally the formulation and the way in which we approach this problem now is one using our prior knowledge of simultaneous equations. We no longer need to have knowledge of sequences and series to understand the problem from here, and that's a nice thing. So what we're going to do is we are going to solve for a and d using these 2 numbers. Now, one method that comes to mind, again there are 2 methods here, we could use substitution or elimination. I am more in favor of using elimination, only because I see here I've got 10a and 20a. So if I multiply this side of the equation, or that equation at the top, equation 4 by 2, and then I subtract them from one another, then I'm going to get cancel out the 20a and the 10a here. Sorry, and the 20a and the 20a. So taking 2 times equation 4, so multiply this equation by 2, and subtracting it from equation 5 gives us, okay, so here notice what I've done is 20 minus 2 times 10a, just cancels out the a's, but now we're left with 190 minus 2 times 45d on that side of the equation, on the left-hand side, and 420 minus 2 times 110. So then doing a bit of simplification here, we've got 190d minus 2 times 45. That gives us 100d. And then when we've got 420 minus 2 times 110 here, that gives us 200. And so now I've got 100d is equal to 200, and that solves to be d is equal to 2. And now we can substitute that expression into equation 4 again. So what I've done here is I've got 10a plus 45 times 2 is 110. And so when we solve for a here, 45 times 2 is of course 90. So take 90 to the other side, gives us 20 on this side. So we've got 10a is equal to 10a is equal to 20, which gives us a equals 2. We haven't solved the problem just yet because we were asked to find the 30th term in the sequence, and that's exactly what we're going to do. Here, S30, now we can actually substitute in all our numbers into that top equation there, because we have A, we have N, and we have D. So now it just becomes a matter of substituting those in. We've got putting 30 for our N, 2 for our A that we derived, and D for our 2. And that's what we get, the expression down there, and that gives us 930. And that concludes that problem.